This lecture is entitled Average versus Instantaneous Velocity. I think we have all probably heard of the term velocity. Maybe we've used the word speed, how fast you're traveling. Velocity and speed are not exactly the same in physics, but for us, they're pretty interchangeable, but we will be using the word velocity here. So velocity is defined as a change in distance per change in time. If you're traveling, let's say you're on vacation and you travel 480 miles during a 12-hour period, then your average speed or velocity is 480 divided by 12, which is approximately, or is exactly 40 miles per hour. Now you say that doesn't seem reasonable with interstates and things, but taking into consideration you're stopping, you're sightseeing, you're shopping, you're eating during that 12-hour period. But the average velocity in that case would be 480 divided by 12. And that's what we're talking about. And that is something that you probably already knew before we started this lesson. So we have here, let's do some talk about terminology here. As I said, most of us are familiar with average velocity. We're going to let the letter S represent distance and T represent time in our discussion here in this lesson. You might say to yourself, why are you using the letter S for distance? Why don't you use D for distance? Well, D is already taken in calculus. We haven't gotten that to that point in this lesson. This is one of the early lessons, probably for you. So we're not going to be able to use D because it would be very confusing. So we're going to use S, but it's not just at random. Let me just share a little bit with you. Patient, there's a Latin word, it's spatium, S-P-A-T-I-U-M. Spatium, S-P-A-T-I-U-M. And in Latin, it meant distance, it meant space, it meant interval. And so it seems reasonable that maybe early mathematicians chose S to represent distance. That's just a point of information that you may find interesting. So we're going to we're going to make a note here that T is time, and T sub 1 here, T, that is we're using that to represent our initial or starting time. That's when we began our journey. And T sub 2 is our terminal or ending time. That's when we stopped our journey. And so the average velocity is S of T sub 2. In other words, this is your distance function. S of T is your distance function. You're familiar with f of x being a function, f being the equation, x indicating that's the unknown. So here we have S of T is our function, S is our equation, and T, it's in terms of T. So it's S of T sub 2. That's how far we went. S of T sub 1, that's our starting point. And verse over T sub 2 minus T sub 1, that's our ending time. That's our starting time. So it's the change in distance over change in time. Now, if you really study this, if this were in terms of f and x, f of x, which you're more familiar with, this is nothing more than y2 minus y1 over x2 minus x1. In other words, average velocity is slope of a straight line. And that's interesting. And we're going to use that fact quite a bit in developing calculus. So let's look at an example here. We have that distance equation is S of t is 25t squared, and t is between 0 and 2. Okay, 0 and 2. That's that time. Now, we're not putting any units with this. In other words, we're not saying this is 2 minutes, 2 seconds, 2 hours, 2 days. That's not important to what we want to do here today. So we're not attaching limits, units to our time, excuse me. And so we want to find the average velocity. This is just a simple problem. To use that equation we just had back here, which is S of t sub 2 minus S of t sub 1 over t sub 2 minus t sub 1. So what we do is S of 2 is 100. In other words, you put 2 in for t, you square it, you get 4 times 25 is 100. S of 0 is 25 times 0 squared, or 0, over the change in time, which is 2 minus 0. So this is 100 over 2, or 50. And this is, by the way, this is your average velocity. And this is also the slope of the line connecting the beginning point with the terminal point on this graph. We'll look at the graph of this in a bit. So that's your average velocity. However, you're not here to find average velocity because you know that from previous courses. Okay, maybe as far back as elementary school, certainly middle school. What we're interested in is determining the velocity at some time during that trip. Not at 0, not at from 0 to 2, but how about somewhere along the trip? What was our velocity then? Of course, if the graph happens to be a straight line, that's no problem, because that is the average velocity. Let's consider the following example. Example 2. S of t is 25t squared, and t is from 0 to 2. Well, that looks like the example we just worked. Well, it is. However, it's different. We're not asking here for average velocity. We want the velocity when time is 1. Now, first of all, let's recognize that S of t is 25t squared is not a straight line. To be a straight line, it's got to be in the form of y equals mx plus b, would it not? This is more like y equals x squared, which is a parabola. And again, I tell you, we'll look at the graph before we're through here. So this is not a straight line, which means the slope is changing as you move along the graph, depending on where you are on the graph. So how are we going to find the velocity at time 1? Well, we're going to use something that we talked about in an earlier lecture, and that is that a curved line is nothing more, if put under the microscope, but a lot of little straight lines. And we don't know how to find the slope of a curved line, but we can find the slope of a straight line, i.e. y2 minus y1 over x2 minus x1. So what we're going to do is we want to find the slope at 1. So let's take a point very close to 1, like 1.1. And let's find the slope of the line connecting 1 with 1.1 using this function. So what we'll do is we'll use our equation and we'll put 1.1 in for t, minus, and then we'll put 1 in for t, over the change in the times 1.1 minus 1. So that means when we put 1.1 in for t, we have 25 times 1.1 squared minus 25 times 1 squared over 0.1. And now we're going to use our calculator, or you can do it by hand. It's not a problem. We're going to square 1.1 and multiply by 25, and we get 30.25 minus 25 times 1 is 25, and we subtract the 2, we get 5.25 over 0.1. Now 0.1 is 1/10, 1 over 10. And you know from study of fractions in elementary schools that when you divide by a fraction, you invert and multiply. So we'll invert 1/10 and call it 10 over 1 and multiply times 5.25, which means move the decimal point 1 place to the right and we get 52.5. And that is what we call the approximation of the instantaneous velocity, the velocity at 1. Now, it's not exact, is it? Why? Because this line from 1 to 1.1 is that is a straight line, and for visually, if we looked at it, you could not tell that it's not curved in itself. But it's not, it's a straight line. So this is an approximation because our closest point we chose is 1.1. Now, had we chosen 1.01, it still wouldn't be exact, but it would be a closer approximation. Now, what we've done in example 1 and 2, we're going to do throughout this lesson that you're viewing. This is a formula we've developed. In other words, this says what we just did. In other words, we chose a point close to 1, 0.1. That's a lot of verbiage. And we like to have things that are a little more crisp. So what we're going to do is we're going to write this, what we just did is S of t plus a, where a is in that previous problem 0.1. But it didn't have to be 0.1. We said it could have been 0.01 or anything. Now, we are saying we'd like for it to be a number between 0 and 1. So, because we want it close. We want it close to the number we're interested in. And so the formula is S of t plus a minus S of t over t plus a minus t. That's the formula. Now, we mentioned this and we've highlighted this. This, what you see right here before you, is going to be very important soon in this course. We're going to use this formula to construct what calculus is all about. So this is very important, and that's why it's highlighted here. Next, we're going to look at a graph. The graph will give us a visual representation of example 1 and 2. You'll see in the graph, part of it's a dotted line. That's your average velocity. Part of it's a solid line. That's your instantaneous velocity. Now, I want to make one last bullet point here. If a graph goes between 2 points, no matter the shape, and if it's a distance equation, the average velocity is always the straight line joining the beginning point, starting point with the terminal point. That's important that you make note of that. That the average velocity is always the straight line that joins the starting point with the terminal point. So here's a graph of what we're talking about. This is a parabola, okay? And this is the average velocity here, that dotted line. Now you'll notice if you were using your calculator, you wanted to go from just so that everything was to scale, you really wouldn't be able to see much of what you want to see of this graph. What we've done is we've altered the scale. You see, this is not to scale. This is your y-axis typically, and look how many units we have on the y-axis. Up to here is 100, and this is your x-axis, and out to here is 2. So if this is 2, this is 100, something's not to scale, is it? And it's not purposely designed like this. Otherwise, this graph would be of no interest to us because it wouldn't show us anything that we could probably glean information from. Now, this is the line tangent to the graph. That's the slope at t = 1. So, okay, makes sense, I hope. And we could count off the rise or run of each of these lines and see that it supports the answers that we had, but we're not going to take the time to do that. But I will indicate here, you know, that point we chose close to 1.1. See, that's right where my pointer is right here. It's very close. Basically, this blue line, this solid line, and that little line are basically the same, but not exactly. Not exactly. But that's visually what we're doing here. Now we'd like to look at some examples, and every example is going to start out the same. The examples change, they show different things, but the first step, which is called the setup, is the same in every one of these. Each of these examples is going to ask you to find the average velocity and the instantaneous velocity. So we start out with a distance equation. S of t is t cubed minus 2t squared plus 5t, much like the one we just did, but a little more complicated, third power. And so let's look at this problem. Now, for average velocity, this is what you do. You take your distance equation. It's s of 5 minus s of 0 over 5 minus 0. That's all there is. And now what you do is you put 5 into this equation, and we're not showing all the cubing and everything. We've done it and for you, and that turns out to be 100 when you put in 5. And of course, when you put in 0 and do all the arithmetic, you still get 0. So this is 100 over 5 minus 0, which is 5. And so 20 is our average velocity. Now we'd like our instantaneous velocity at 3. So we're going to choose 3.1 as our closest point. Now, again, you don't have to choose 3.1, but we're going to make our closest point 0.1 units away for consistency in this entire lesson. And if we were asking you to work a problem for us, we would probably, if this were a classroom situation and this were a quiz question or something like that, we would probably ask you all to use the same point. Can you guess why? So that everyone would get the same answer. A class of 25 or whatever might be in your class, we don't need 25 different answers, which is what we could get if everybody chose their own nearby point. So just want to clarify that. Now, that's going to be S of 3.1 minus S of 3 over 3.1 minus 3. That's your setup. That shows that you know what you're doing. Okay, hopefully. Now, this number is gotten from putting 3.1 into this equation. And we've used our calculator to do that. It's certainly possible that someone could cube 3.1, but why? Just let our calculator do the work for us, because we've shown we know what we're doing. We put 3 in and we get 24. And of course, the difference of these two is 0.1. And we said that earlier. If we looked at the previous, when we had our formula. And now we simply subtract, divide by 1/10, which is multiplied by 10. That's nice of being 1/10, and that's our instantaneous velocity. Now, it's an approximation. That's why you see not equal here. It's an approximation. Now, again, I want to reiterate, this really, if you've got a calculator in hand and you're following this procedure, the setup, you should be able to do the rest of the lesson yourself. But we're going to move on. But I want you to realize that every one of these problems in spirit is the same. And so you should, after you work all of these problems and then maybe a few others that might be assigned to you in your course, have this down without just turning it into a rote memory task. Here we have another equation. This one is S of t is 1/2 t squared minus 3t plus 2, and our time goes from 1 to 7. So a little different here in that the time is not 0 starting, and we have a fraction in it, and that gives some people pause, but should not, especially if we've got a calculator. Average velocity is f of s of 7 minus s of 1 over 7 minus 1. We've put 7 into the equation and we've gotten 5.5. We've put 1 into the equation and we've gotten negative 0.5. And this, of course, is 6. And then when you subtract here, a little harder here because you got to remember from algebra that minus a minus is a plus. So this is 5.5 plus 0.5 is 6 over 6, which is 1. That is average velocity. In the second part, we want the instantaneous velocity when t is 4, so our close point is going to be 4.1. The setup is the same, s of 4.1 minus s of 4 over 4.1 minus 4. We put this 4.1 into this function and do the arithmetic. We get this. We put 4 into this function, do the arithmetic, and we get this, negative 2, and then minus 1.895. Minus a minus 2 means add 2, and so we get 0.105 divided by 0.5 is 1.05. That's an approximation of your instantaneous velocity. Okay. Now, example 5, we're throwing in example 5. We hope you all understood the first 4. Example 5 is to remind you, and if you didn't already know, that we're not just interested in functions that are in terms of that are polynomials or algebraic, what we call algebraic equations, such as square root of x, cube root of x, x to the 5th power, things of this nature. We're interested in exponential functions, trigonometric functions, and logarithmic. So what we want to do here early in the course is introduce you to remind you of that. So we have s of t is e to the 2t. E is an irrational number between 2 and 3. And e is on your scientific or graphing calculator. Not if you just have a full function calculator, but so to use your calculator to do a problem such as this, you probably will need, if you want to get cut down on the arithmetic, you do want to have a scientific or graphing type calculator. So, but here's the thing. No matter whether you consider yourself good in math or poor in math, we all start at the same place. We all have to know this setup, which is S of 2 minus S of 0 over 2 minus 0. Now, when you put 2 in for t, that's e to the 2 times 2, or 4. And when you put 0 in, that's 2 times 0, which is 0. And so this is e to the 4th minus 1 over 2. Now, that's your exact average velocity. If you want a numerical answer, although this is a number because e is a number, but if you would like a rational number, say here, which this is rational, can be written as a fraction, then you're going to have to use your calculator to get that. And this becomes an approximation because we've rounded this. Now, if you want instantaneous velocity at, say, t equal 1, we're going to use that test point. Nearby point is 1.1, like as usual. So we put 1.1 in for t, and that gives us 2 times 1.1, or 2.2, minus e squared when we put in 1, and over 1.1 minus 1.1. And you can write this because this is dividing by 1/10, which means multiply by 10. Now that's your instantaneous velocity, an approximation of it. Even that's not the exact instantaneous velocity. We're not finding in this lesson the absolute instantaneous velocity. Okay, that comes later. Okay, now if you want to get a decimal approximation, then you're going to have to use your calculator. And this is what you would get when you put e to the 2.2 in, gives you this, and e squared gives you this. And so you've got to use your calculator or stop here. And the instructions of the problem will tell you whether they want you to give it as a decimal approximation or they want you to give us as exact an answer as you can, and you have to follow the directions of the question asked. Okay. Now, example 6, we would like to do a trigonometric one, and this is the sine of t over 2, where t is between 0 and 3 pi over 2. The reason we've chosen 3 pi over 2, you have had trigonometry. That's a prerequisite for most calculus courses. And so you know that in trigonometry, so that the teachers insisting that you not use a calculator, their important values are 0, pi over 6, pi over 4, pi over 3, and pi over 2. Because we pretty much, after studying trig, we know those values for the different trig functions. So we're going to abide by that in this sample problem here. So this is a lot busier looking. When you look at it, it's s of 3 pi over 2 minus s of 0 over 3 pi over 2 minus 0. That's just filling into the average velocity equation. And right here, what we've got here, this is, remember, this is s of 3 pi over 2. But this is t over 2. So if t is 3 pi over 2, 3 pi over 2 divided by 2 is 3 pi over 4. And the sine of pi over 4 is square root of 2 over 2. Now, we don't have pi over 4. We're not going to reteach the trig here. Turns out that 3 pi over 2 is in the second quadrant where the sign is also positive. So we're not showing all the work here, okay? We're not trying to teach a trig course here, but I did want to explain to you how this turned out to be a form of pi over 4, and it's because a lot of people think this is 3 pi over 2, then I've made an error because it's 3 pi divided by 2, but no, this is t, which is 3 pi over 2 divided by 2, is 3 pi over 4. And it's important you note that. And that's why you're listening to this. And this is why this problem is so much more difficult than the 1, 2, 3, 4, because you have to understand a little bit more about mathematics. Okay? But we want those of you that are really at the introductory level and maybe have not as strong a background in some areas of math as some other. We want you all to have problems that you can find your comfort level with. And certainly we would say 1, 2, 3, 4, do that. But you need to those moving on with mathematics need to not skirt or duck problems like this. We all need to look at these. And then if you have instantaneous velocity and we wanted it t is pi over 2, then we have closest point is 0.1, so that's going to be pi over 2 plus 0.01. That looks messy because, see, pi over 2 is not a decimal number. So we have to, this is the setup right here, okay? And then we've done all the particular, rewritten this is pi over 2, pi over 4, because remember this is pi over 2, which is pi over 4, and 0.1 over 2 is 0.05. And you see for yourself, you can look at this, the arithmetic that's going on. And of course, to work this particular problem, as we are doing here, you must have a calculator to get the answer. So for those who say, I never use a calculator, are going to be stymied by doing this problem here. Now, this pretty much is the last problem we're going to be doing. But I got a few closing remarks I want to make to you. These problems seem very time-consuming, do they not? And I would have to agree. But we said earlier in the course, and we keep repeating it in this series, if something takes a long time to do, seems very tedious, there must be a better way, and that's what you're in the calculus for, is to find a better way to do these problems. In fact, each of these 6 examples can be done as far as finding the instantaneous velocity in less than 30 seconds, eventually. Not today, not in this lesson. And in fact, when you do it in 30 seconds, not only are you going to get the answer faster, but in the case of instantaneous velocity, you will get it the exact answer, the exact instantaneous velocity, not a close approximation. So there are a lot of good things on the horizon. This is a very important lesson because we will be using this lesson. We will refer back to it, at least 2 different equations. When we develop what's called the derivative, we're going to refer to this lesson. And when we study something later called the mean value theorem, we're going to refer to this lesson. And when we talk about acceleration, we're going to also tie it into velocity, which is what this topic is all about. And we simply mention those things to let you know that this work is done for a purpose. Without what we've done in this lesson, we would not be able to develop the very more fun ways of doing the problem using calculus. And so you have to go through a lesson like this, and we do this on many occasions. But there's always good news at the end. So this concludes this lesson.